All right, we'll get going in the next section here, module 4 for energy literacy. One quick question from Aaron. Will the slides for these presentations be available for viewing after we're done? I don't think we talked about the slides themselves, but one thing we are doing, you'll see this webinar is being recorded. So what we're going to be doing is in the future, these videos will be of the recordings will be available on YouTube. And hopefully not too far into the new year. So that's the plans, and I think we can have some conversations internally about how can we distribute the slides themselves, because there's a lot of valuable information just within these slides. So let's get on to energy literacy here. So energy literacy, one of the things we're looking at is how does the energy equation really fit into these deep energy retrofits. So we're going to really talk about electrification of buildings and how that fits into deep energy retrofits. Electrification is a main item of conversation in industry right now. So we're going to touch on kind of what the current energy profile is in industry, and primarily in Canada, or with homes and industry. And then we're going to be looking at what electrification means for a building and what are the obstacles and benefits to it, and touch on site energy production, so solar, and then look at, with electrification in mind, what are those energy conservation considerations we need to take into account for deep energy retrofits. So starting off, we want to look at what types of energy are used in a home. For 90% or more of Alberta and much of Canada, it's electricity and natural gas are the energy uses that are coming into our homes or buildings. And then with that electricity, that comes from a lot of various sources, from natural gas prevalently in Alberta, coal. Some parts of North America are still prevalently coal for the production of electricity, but a lot are phasing out, such as Alberta. We're not too far away from having coal fully offline in Alberta. And we also look at those renewable sources such as wind, solar, hydro, and geothermal. And one note is that the electricity sources such as hydro, solar, wind, and nuclear have no greenhouse gas emissions during operation. But geothermal is something that it's kind of an outlier. It's becoming more used. There's costs related to it, but some geothermal power plants may have some emissions due to the release of sulfur dioxide or carbon dioxide, depending on what heat sink they're utilizing within the earth. And then one thing we look about in Alberta, there's a lot of conversation of that transition from coal to natural gas. And in preparing this, I was looking at what's the real comparison between the two. So we can see, like, natural gas is far less than half the emissions of coal per kilowatt hour. So great improvement on that, but we still have that 409 grams of CO2 equivalent per kilowatt hour of electricity generated with natural gas. So there's room to still go. We look across the provinces in Canada, we have a wide variance in the emissions of the different electrical grids. Alberta used to be a lot higher on the list a few years ago, and these are numbers just out of 2021 from Canada's greenhouse gas inventory. So Alberta is getting better, still not as good as a lot of these other provinces that are primarily hydro in their generation, but we have renewables as well that we can look at. And here we're looking at how Alberta's grid is improving over time. We want to continue to see that downward trend. One of those things we look at for that downward trend is the installed capacity. How much energy can we generate? So capacity in this pie chart here is looking at if each of these sources, generation stations, were generating at 100% of capacity, how many megawatts would be generated? So we can see we've got 17% capacity in Alberta through wind, 7% through solar, hydro 5%, natural gas 61%, coal 7%. But one of the things we look at as well is what are the uses and what are the considerations for each of these sources and how they generate electricity. How do these power plants work? With wind, we have 17% capacity of wind, but that's only generating when the wind's blowing enough. Solar, we need the sun to shine. Natural gas, we have 60%, 61% capacity, and a portion of that capacity is just peaking plants to meet time of use demands on the grid. But so these numbers are from Alberta Utilities Commission. This is end of 2022. What's the capacity in Alberta? Now let's look at what did we actually use in 2022 in Alberta. So we can see there's a big variance. The one that stood out to me that was interesting was the variance in coal is 13% of what we actually use compared to it being only 7% of the capacity we have on the grid. So this is something we need to keep in mind. And I think it really points to the point, or to the fact of, let's look at reducing our energy needs in the first place. And then let's talk about where that energy is coming from. So if we look at where that energy goes in Alberta, the electricity that's generated, 20% of that is residential. And we have commercial and industrial. We look at those 2050 goals. We look at all segments of industry, all segments of the country hitting net zero emissions. So hopefully all of these segments of electricity use, they're going to gain efficiencies. They're going to look at ways to decarbonize their sources of energy as well. Then we look at that residential energy use, which Dina touched on this earlier. Significant amount of that is space heating and water heating. We have paths that we can improve that, but what's the most feasible metric for that? When we look at a deep energy retrofit, we're mainly looking at that insulation and air tightness to reduce the heating loads. And then after that, we look at how can we use efficient heating, ventilation, and air conditioning systems to meet that lower heating demand. One of the things that Dean mentioned earlier is that now cooling demand is becoming a larger component in the conversation as well. And we're not just concerned about heat in the summer, in the wintertime, but how can we also cool in the summertime? So once we look at having that airtight, highly insulated envelope in a building, we look at highly efficient HVAC systems to provide that lower amount of conditioning that we still do need. Then we want to look at utilizing renewables to meet that demand and hopefully achieve a target of net zero on-site energy for that home. Now, a key option to be considered when we're looking at all this is electrification. So we look at electrification, that's eliminating all fossil fuel or natural gas consumption within the home, or other fossil fuels as well beyond just natural gas. Primarily, we're looking at heating, hot water, cooking, and fireplaces in many homes as well. And we switch those to just use electricity in the homes. So within this section here, we're drawing on a lot of information that comes from Passive House Alberta. By the time we have these videos listed live, their final report will be available on their website, and that's through funding they receive from Alberta Eco Trust. So how can we look at electrifying single-family homes without upgrading the service, which we'll get more into that in the coming slides here. So why do we want to electrify? There are several advantages to electrification. It provides the ability for all home systems to run off of on-site produced or purchased renewable electricity. So if everything runs on electricity in your home, you have enough solar panels on your roof, there can be many days out of the year where you're fully self-sufficient. You're not drawing on the grid at all. There's certain sense of satisfaction we can achieve from that. We have the health advantages, improved indoor air quality through not having combustion gases in the home. There's been a lot of articles in the news and health reports on the impact of natural gas stoves and ranges in the past year. And there's also that safety factor. There's that certain fire risk from having natural gas in the home and the different appliances that run off of it. If we remove the natural gas, we remove those risks as well. When we use efficient electrified appliances, generally there's a decreased overall energy use through those, particularly when we look at using those heat pump components, as opposed to natural gas furnaces or natural gas dryers. And also when we look at electrification, we can eliminate the entire natural gas bill, which is not just the natural gas fee itself, but also the administrative charges as well. As we can see on this pie chart here, in that deep green, that's what we're paying for with actual cost of gas used. We have the carbon tax and a lot of other fees as well. But if we remove natural gas from our homes in its entirety, we're removing all of these costs on a monthly and annual basis. So there's that small financial benefit to it as well. Some disadvantages to electrification. Depending on the greenhouse gas intensity of our grid and other conditions, electric heating may not be the lowest emissions option. Grids are getting better. I believe in Alberta, with our grid, we're pretty close to neutral. We switched to electricity. Our grid's not the greenest. We're 400 and change in grams of CO2 per kilowatt hour, but still with the efficiencies of a heat pump or air source heat pump for space conditioning, we are around the break-even mark for emissions compared to natural gas. But as the grid gets greener and times of year where we are running off that solar on site, it is a greener option. The other key consideration for electrification potential disadvantages is that depending on the electric resistance backup, and I touched on this earlier in the Q&A, depending on what we do for backup heat, if it's electric resistance and at what temperature that comes on, how does the weather go for a year, that backup heat can lead to a significant amount of electricity use. And in some homes in the past that have transitioned to net zero and have electrified using everything air source heat pump, and they haven't necessarily, it could be a sizing or installation issue with the heat pump components or their heating components, and it could be commissioning, and it could also be didn't improve the envelope enough. But there are homes that have experienced higher energy bills after they've retrofitted to a net zero level of performance, and that's not what we want in this industry. As we're looking at retrofitting homes and electrifying, we want it to be cheaper to operate these buildings afterwards, not more costly. And then, so as we get into this, let's dive in a bit deeper and look at what are the electrical loads that we're using as we electrify. So we've touched on space heating, which is primarily the air-to-air heat pump, which is most commonly used. We can do air-to-water that uses a standard outdoor unit and can tie into hydronic heating elements within the home. And then there's ground source as well. It seems most common in retrofits is using a heat pump tied into an existing furnace or a new blower furnace cabinet. And then we're using all the existing ducting within the home for the space heating. And we look at electric resistance for space heating as well. There's a small segment of the market that looks at, let me improve my home enough so that I just need a few small electric baseboard heaters around the house to meet my heating demand. That is often a significant amount of insulation and may not be practical in many instances, but that does definitely simplify the heating system to a few heating units that cost less than $1,000 to heat your entire home if you only need several electric baseboards for installation costs, that is. And we look at domestic hot water heating. So we have the heat pump hot water tanks, which the industry is largely moving towards. And within recent months, there's even some 120 volt standard plug-in heat pump hot water tanks that are available if it meets what an occupant's or homeowner's hot water usage profiles are. So not going to have the response rate of a higher amperage heat pump hot water tank, but they can be smaller and it can fit within your electrical panel. We'll get into that a bit more in a bit here. And then there's the standard electric resistance hot water tank. There's some super high efficiency options, which are mainly high efficiency in the amount of insulation they have and the different ways that they can work, but it still is that electric resistance. So you're looking at a 1-to-1 energy in, energy out for the heat in there. Other loads we look at adding when we electrify: EV charging, an ERV or HRV, electric range, or an electric fireplace. And then the other question is optimized electrification, which is a term that Passive Alberta is kind of coining through their research, which is when we can electrify a building without needing to change the service to the site, whether it be the meter or the panel. We can just keep those as existing and not have to upgrade. That is ideal. A lot of buildings to date, a lot of homes to date in Alberta that have electrified, it's the standard course to upgrade from a 100 amp panel in service to a 200 amp panel in service. Then you have room for everything. But that can be quite costly. And the question is, and what we're addressing here is, how can we do that with just maintaining the existing panel? How can we electrify and maintain our existing panel service? And I got ahead of my slide here. So when we look at that site service, it's important to look at what is the homeowner's responsibility and what is the utility's responsibility. This is a graphic from Redwood Energy in California. They've done a lot of great work on energy efficiency. They've created the Watt Diet calculator, and they have a lot of work on electrification as well. So we can see here in the blue, these are all that, and it might vary slightly depending on utility and location, but generally all the blue is what the utility owns. And the reddish there is what's customer owned or what's homeowner owned. And so any cost to upgrade the red is borne by the homeowner directly, and the blue borne by the service provider or the utility. But in most cases that might be a one-time upcharge, or it would be added to the other fees on neighborhood electrical bills to cover the costs. Any costs that the utility incurs is going to be passed on to the end user. They're not just going to pocket it and take it out of their profit margins. I might be getting a bit too political with that statement. But generally, when we look at our site service, that's everything from the electrical panel all the way down to hitting the main service wires leaving the home. And when we look at needing to upgrade the electrical panel on site service, standard upgrade typically costs between $3,000 to $7,000. That's if everything is perfect and works right. If there's the need to replace the service wires between the panel to the meter, or the meter to the main service wires, that can be significant, especially if some of those wires run underground and aren't in a conduit. So there's a lot of potential costs when it comes to upgrading the site service. So best to avoid it wherever we can. Now, when we look at whether or not we need to upgrade a service, we need to look at what the capacity of our electrical panel is. There's a lot of or not precise, but slightly complicated calculations dictated in the Canadian Electrical Code, and they should be performed by an electrician. Key considerations to keep in mind is that loads on a panel less than 1,500 watts are not counted. Not all loads on a panel are counted at 100% towards that panel capacity. And some loads can be excluded from load calculations if you use a load share device, which we will get into load share devices in just a minute here. So load share device basically allows two loads to be controlled on a single circuit. There's two main types. There's a primary and secondary load share device, and then a circuit positive load share device. Now with a primary and secondary, you have a primary load, typically electric range, or maybe it's clothes dryer, where that is the load on that circuit that it is one that needs to be powered all the time. And then your secondary load will only receive power when the primary load is not in use. So thus, you can have two loads on an existing 30 or 40 amp circuit breaker. You don't need to add a second one. And you just need to pair what the uses are on there to make sure they're not items you're going to want to use at the same time very frequently. So in the illustration, for example, your EV charger can come on at any time. It doesn't need to be right when you plug it in. It can come on through the night when you're not drying clothes or cooking dinner, for example. But there are some units that will maintain a small 100 watt power to both sides of the device. So if you're concerned about digital clocks on your range being reset, then that is able to be addressed as well. And one of the things to look at too is to utilize loads that are sharing through these devices that have similar loads. So you have two 30-amp devices rather than like a 60 amp, and a 20 amp may not be ideal for that. And using similar devices or similar load devices allows you to kind of maximize or optimize the use of a load share device within that panel sizing as well. So the cost for a primary, secondary load share device is between $800 and $1,000 supply only. There are several options in the market already. The other option is a circuit pauser load share device. Now, this is something that's connected to a specific circuit, and it monitors the whole home energy use of the panel. And when that energy use reaches a certain threshold, typically 80%, it will cut off that controlled circuit. It will pause it until the whole home energy use drops below a certain threshold for a period of time. And then it will allow that device to be used. And these are similar in range for cost, $800 to $1,300. The one thing to consider between a primary, secondary device versus a circuit pauser is that a circuit pauser is typically still one load per circuit on your panel. So you might have that actual space consideration within some panels, where the primary, secondary device, you can get two loads onto a single circuit on your panel. Another option to look at is smart electrical panels. Now, this allows a whole lot of control and nerding out. If you're a smart home geek like myself, you can look at circuit by circuit monitoring, control, and prioritization. So you can say, you can set your maximum load on your panel. I only want to have 80 watts peak coming off this. And if my electricity use is coming above that, then these are the circuits I want you to kill first. And if I'm still using too much, then kill these other circuits or pause them. So a lot of benefits available through electric panels. And there are a few options on the market right now. Leviton seems to be one that has more standard, something that fits kind of what we're used to. You basically get smart breakers in their standard load panel, and you purchase their hub as well, which has current transformer monitors for the mains coming off the panel. And some of these units can be quite costly. The Leviton really allows that cost to be directly related to what you need, not fitting within other smart panel manufacturers and the 2 or 3 options they have for panels. And there's one of the manufacturers out there where the smart panel actually piggybacks on the existing electrical panel as well. But whether you do a smart panel or a load share device, electricians are going to be needed to install those components, any hardwired components, or also any appliances as well that are hardwired. Electricians are needing to do that work and do it properly from a safety standpoint. And also, as mentioned before, they're the ones that need to complete the load share calculations as well. Now, obstacles to electrification, there are a few that we look at. If we can't optimize and maintain the panel, there's going to be that cost to upgrade the electrical service. If we need to have upgrades on the distribution network beyond the home, that is going to be something that will be passed back to the homeowner or to the neighborhood in one form or another. Currently, this is a smaller problem, but when we look at how does that work in a neighborhood, it might not be as small of a problem as we think. We talk about the first couple homes on a transformer being able to get away with a service upgrade, and it's still within the transformer's capacity. But once a homeowner wants to upgrade their service and it requires a larger transformer, then that cost is going to be kicked back to the neighborhood. And to give a little bit of a small picture of scale for that, on my block there's about 40 homes and there are 4 transformers, so it's about 10 homes per transformer to meet that capacity as the grid in my neighborhood was set up in the 80s. So it's a question of how much capacity is left with 10 homes per transformer. So where we can optimize and not need to upgrade our service, I think that is key to reduce the costs of electrification. Other concerns is looking at the lack of space for the added or larger mechanical components that we're looking at, primarily heat pump, hot water tank. These can be larger in many cases from a traditional natural gas hot water tank, because you have that heat pump unit that's installed on the top. And then, like I mentioned earlier, for my house, where are we fitting a heat recovery ventilator, energy recovery ventilator when we electrify and look at those components as well. The other thing, which was touched on earlier, is that possibility of higher utility costs due to increased electricity usage. Natural gas is cheap in many locations, primarily Alberta, especially compared to our high electricity costs lately. So how do we increase our improve our energy use, improve our efficiencies as part of that electrification strategy, so that we're not being left with the higher operational costs for the homeowner after they electrify, where this thing they thought was a great idea is not being the best idea for their pocketbook. So these obstacles or concerns can be minimized or avoided by improving our building envelope to minimize our peak heating loads. I think this is one of the key components. Anything we do to a building envelope, we do it once, we do it right. It doesn't need to be touched for 20, 30, 40 years or more. Whereas any components we have in the HVAC or electrical, many of those do require maintenance over time, and is something we're going to have to keep in mind. And there's costs related to that. And how can we utilize air-to-air or ground source heat pumps for heating and cooling, and optimizing the envelope so we don't have a significant backup heat that we have to meet in the wintertime when it gets below those operational ranges. We can also look at minimizing costs through using high efficient electrical appliances. There's induction stoves, there's heat pump or condensing clothes dryers, and you can even get condensing washer and dryer in one for your clothes. So one unit, pretty much the same cost as a traditional higher end, mid to higher end washer. Put your dirty clothes in, they come out clean and dry. Less effort on our part to get our clothes clean, and also it saves the room in our laundry rooms as well. So a lot of great solutions that have other benefits as well for improving the efficiency of these units. And then we get into on-site production. So producing renewable energy on site is a key aspect to achieving that net zero status. Small scale wind and hydro aren't really feasible in many cities and locations unless you've got a remote acreage with capacity. You're going to be looking at solar. So really quick, for those who would like a refresher or haven't had the chance to dive into it before, let's get into the basics of what solar or photovoltaics is. And that's looking at the conversion of light energy into electricity through semiconductors. Standard solar system has panels on the roof, and then which generate electricity in direct current, and then utilizes an inverter to convert that to an alternating current, which is what our household electrical system utilizes. I have a video here to look at basic science behind a photovoltaic cell. Get it to load. It's 5 minutes. 9 minutes. 5 minutes long. Actually, what I'm going to do in interest of time, go to YouTube and Google how do solar cells work? If you really want to know. So main parts of a solar PV system, there's the panels on the roof, there's the inverter converting the direct current to alternating current. When we look at solar from a grid tied standpoint, we have a bidirectional electricity meter. This allows electricity to flow both ways, both out to the grid and come in from the grid when the solar panels aren't producing enough. And it meters kind of that net value of what you're importing versus exporting. There's multiple safety components in the solar system as well, to provide safety for the homeowner and also for those working on the grid in case of a power outage. Solar systems, many people don't know that if you have a grid tied solar system by default, if the power goes out on the grid, your solar system is going to go down as well. Unless you get a grid disconnect installed as well, which is a several $100 component to be added to the system as well, which will allow your home to island to be separated from the grid in the event that the grid goes down. Some homes we want to look at batteries, regulators, and charge controllers as well, to how can we store some energy in our home to use when we're not producing directly. Currently, due to the financial implications of batteries and systems, they're not very widely used, but they do have their place and some advantages. So let's look at string inverters versus micro inverters. Transitions on these slides are a bit clunky. So in a string inverter versus a micro inverter, string inverters utilize a single inverter component, which have multiple strings, or typically it's a row of panels that are connected to it, and go into the inverter, which is typically located in electrical mechanical room, or sometimes it's outside close to the electrical meter. And it's at that inverter where you convert the direct current to alternating current. One of the main concerns with the string inverter is that if you have shading on some of your panels, it can knock out an entire string, because in a string inverter, all the panels are connected in series. If one of those panels gets knocked out for the energy production, it'll reduce the performance of that entire string that's connected to the inverters. Another minor item too, is sometimes the string inverters can have a bit of a hum or buzzing noise, especially on the larger capacity ones. When we look at a micro inverter, this is a smaller inverter. It's installed right at the panels. You can connect 1 to 4 solar panels to a single micro inverter, depending on the specific model. And that direct current is converted to alternating current right at the panels. And then from there, from the inverter onward, it's standard AC wiring in the home. One of the key advantages to microinverters, that can optimize the panel production, especially if you have partial shading from trees or nearby buildings. You can maximize the amount of solar that you produce. And microinverters are very widely used in solar installations residentially right now throughout Alberta and Canada. And there's a couple graphics just kind of illustrating the different components of PV systems. So here's the system with microinverters right at the panels, compared to a string inverter. And then when we look at how to integrate solar PV into retrofits, the key things we want to look at are, do we have a good self-facing roof slope to install solar panels on? You can install solar panels on any roof slope you want, but the ideal is to be self-facing and have a good tilt on it to produce the optimal amount of solar energy from it. Want to be considerate of shading from surrounding structures. And as you can see in the image here, complex roof designs can kind of restrict the number of panels you can fit on the roof. And it's, when we look at planning for solar for a retrofit, an energy advisor can complete some early estimates and rough designs, but the end design and estimates for how the system will actually work should be done by a solar installer. And when we look at utilizing solar to hit net zero on-site energy, to get, if we want to look at getting a net zero home reno certification from CHBA, for example, that system needs to be sized in HOT 2000 modeling through the energy advisor, and you need to get a EnerGuide rating of 0 as part of the process of doing the retrofit. There's other resources out there for planning solar and looking at different consideration. Natural Resources Canada has this planning and decision guide for solar PV systems. And then also through NRCan and CanMed Energy, they have a photovoltaic ready guidelines. So this is where, as part of a retrofit, the funds just aren't there in the budget for solar right now, but what can we do up front to make sure that we're ready for that? So if we're messing with the roof slope, we want to optimize it for solar, get into it, make sure we have electrical panel and bus bar capacity, ensure wall space for the solar components, and ensure all the work we're doing is ready for solar. Couple key considerations is that the larger generation systems can utilize a splitter box as kind of shown in the image there. So we don't connect that solar right to the main panel, but we connect it between the panel and the electric meter. When we use microinverters, that allows all wiring, as I mentioned before, to be AC. When you use a string inverter, all the wiring from the panels to the string inverter is direct current and needs to be run through conduit. So extra considerations when we're planning that. Here's some key metrics or requirements from the building code to look at how much can you fit for a solar panel system tied to an existing electrical panel. And all the considerations narrow down to the fact that within the standard 100 amp panel, the most you're going to be able to fit on that is a 4.8 kilowatt system. And in our experience in Alberta, a lot of the retrofits are people that are installing solar to hit net zero. We're looking at solar systems the size of 12 to 17 kilowatts in that range for the majority of them. So fitting that solar right on the electrical panel is not necessarily an option. So we look at having those tie-ins or a splitter between the panel and the electrical meter. And I think one of the things to keep in mind to kind of close this unit is a quote by Amory Lovins, that the greenest unit of energy is the unit of energy that is never generated thanks to efficiency and conservation. So as we look at electrification, we want to have some considerations that kind of come in the planning stage before we look at, whoops, I went too far back. Before we look at electrification, we want to look at optimizing the balance between required heating and cooling loads compared to the electrical improvements and sizing of components. How can we minimize those peak loads and compare the balance between the cost of a solar PV system install and the cost of envelope upgrades? And then how can we look at improving occupant electric loads? Once we significantly reduce the space heating and hot water heating electrical demands through use of heat pumps, then those occupant loads become more significant. So how can we optimize those? And in all of this, it all comes back to house as a system, which is something we'll be getting into, I believe, tomorrow in the presentations. So that is the main slideshow for now.
Great.
And we have a few questions here. We are at time. I'll bring up the questions here.
Thank you, Ben. Appreciate that. Yes, and yes, if you can stay with us to try to answer some of these questions that came in.
Yeah.
Otherwise.
Doug, I think that's a very good point. Slide 14. Disadvantages when the electrical grid goes down if you're all electric. I would say too, if you have a natural gas furnace and you have no electricity, your furnace is not operating either. There's no mechanism to blow the warm air through your home. So this goes back to needing to improve the envelope in the first place. As I mentioned earlier, if you have an R18 wall, that might keep you comfortable for a few hours in the wintertime. If the power goes out on a -30 day, but if you've improved that wall and you have air tightness, you have an R30 or 40 or better wall, then you can be good for several hours, potentially to the next day or multiple days, depending on a lot of considerations within the home. But anything we do to the envelope of a home to improve its efficiency, reduce its heat loss, that serves us whether or not there's power coming to the home. So yeah, and natural gas outages, I guess there is an option to have something plumbed in directly to a gas line, like a radiant heater or something that can still produce a bit of heat if the power goes out. But yeah, I think it's building in that resilience to the system through envelope upgrades. From Steve-O, with all the information presented, is the technology reasonably available in terms of performance and cost for full electrification in Alberta's environment? Oh, I missed one. I'll get back to Pinellas in a second. Sounds like there are certain risks to go fully electric in terms of temperature extremes and also natural disasters. What happens if you have a very cold period with snow and also an outage in the power grid? Yep.
Same
That
answer.
worst case scenario comes in there. It's like, let's improve the envelope as much as possible. But looking at that though, the envelope upgrades can be costly. And on Friday, we'll have Steve Norris and Tyler Hermanson joining us to go through case studies as part of this. This is what the actual costs were. The envelope, though improving it is great, it is costly to improve the envelope. That's one of the most significant costs in doing a deep energy retrofit. But it does have these passive benefits that work whether or not there's heat or electricity as part of that. Panella says, is there any advantage to a hot water on demand system as opposed to a hot water tank? So hot water on demand or tankless hot water heaters, you can get electric hot water heaters, but that's going to be electric resistance. Another concern with the tankless hot water heaters is the large amount of narrow channels going through to allow the quick heating of the water, and those require regular annual maintenance to keep clean and working optimally as well. And I think the key advantage in moving to a heat pump hot water heater is that heat pump function where you're getting multiples of energy out versus energy in, which we need to take into that house as a system consideration, whereas that is adding to the space heating load to your home as well. So if you're using an air source heat pump for your space heating, it still looks great, but if you're using another mechanism for that space heating, you're kind of piggybacking onto that. The other concern with hot water on demand, they're typically a very high wattage to heat up that water in such a short period, so it can add significantly to your peak electricity demands in the home. And then from Hyro, good to see you on the webinar, Hyro. Hyro is actually a former member of GBT. A couple summers ago as a student. He was helping us out. How on board are the municipalities and provincial government with deep energy retrofits? They're getting more and more on board from a municipality level. How do you answer this one without getting political? There are incentives coming out. The federal government has been great this past year with providing many funding programs to help accelerate deep energy retrofits and improving the systems behind them. City of Calgary and City of Edmonton have been doing great work as well through their climate and environment teams to look at how to streamline things. And we can get into as well on Friday with the actual permitting implications of some of these deep energy retrofit projects. Depending on the method you're going about it with the envelope upgrades, a permit may or may not be required. So they're coming around, and I think we'd all agree that more support is always needed for that. So yeah, Dean, turn it back over to you.
All right, we're just a few minutes over 1 o'clock, so thank you all for those who stayed with us. Tomorrow will be